In the third lecture on artificial intelligence in robotics course, we will focus on path planning, and during this lecture, we will cover path planning, grid and graph-based path planning method that can be used not only in the first task, but can also be utilized in your project on robotic exploration. Let's start with robot motion planning. It's a motivational problem. It is defining the way how to transform high-level task specification provided by humans into low-level descriptions suitable for controlling the actuators. So we are asking to develop algorithms for such transformation, and what we are looking for is motion planning algorithm that provides the transformation how to move a robot or object considering all operational constraints. And you can imagine different application scenarios like robotic arms in the factory, walking robot on the stairs, or any other challenging terrains, or extraterrestrial exploration, where the robot relies on what is sent, or in this Mars rover, also on the commands from the Houston. But here we can consider very well defined environment, although in this particular case probably as well. And the important part is that the motion planning, robot motion planning, consists of a combination of several disciplines: mathematics, robotics, computer science, also control theory. And because the problems are very complex, also artificial intelligence, and in many cases you can rely on geometric representation of the environment, and that's related to computational geometry. The classical motion planning problem can be found in the literature as a piano movers problem. And in addition to this comedy part, we also make a funny example. But in this case, this is the piano that can fly in the environment. But the environment is a real environment. It's the basement of the Charles Square campus, the building E. The main idea here is that for that classic motion planning, we can rely on a model of the environment and also the object piano here. And we are looking to find a way how to move the piano from one place to another without actually hitting anything. So this is the basic planning problem, and we can consider that it is focused on rotations and translations. And motion planning is the way how we find a sequence of motions. So what we need is a model representation and formal definition of the problem, for sure. And we also need a context about the problem, because we need to establish realistic assumptions. Because our plans has to be admissible and feasible, but as we already covered in the previous lecture, all the details will lead to this frame problem. So we like to use what is necessary to use to find an admissible and feasible path, or motion plan. And in the robotic context, we can split the planning path as a mission planning that eventually on the symbolic level as task and action plans, and motion planning where we can consider this simple let's say classification and horizontal sequencing of the problem as a problem in a geometrical level. We have a model of the robot and we have a model workspace, so we perform a simple path planning in a geometrical world. Then we like to have a smooth path, a trajectory, so we create a trajectory from the path, and then we will execute this trajectory at the physical level. The robot control that has this sense and acting, and in a fast feedback control we will follow the trajectory. In the motion planning and trajectory planning is mainly this middle part. And once we have a trajectory, we can consider open loop control from this point of view, from the point of view generated trajectory. But here, controlling the motor, that we will set the command of the trajectory to reach some velocity of the motor, and to reach it, we can have a feedback control. But of course, at this level, on the physical level, we have sources of uncertainties because of real environment, and nothing is perfect. And regarding the path or motion planning or trajectory planning or trajectory generation, you can also think about, like, this is not the way. So maybe this is simpler than creating the trajectory, and we can use some post-processing. But we may also ask for direct planning trajectory. And finally, we can consider all of this as one block, and we can combine it. And these are the trends nowadays in robotic planning or path planning, motion planning, that we as we are asking for better performance, so we need to combine these, let's say, previously individually solved problems. And stay with the real robots, because in real deployment the problem is really complex. The world is changing. The robots needs to update the knowledge about the environment using localization and mapping and navigation, and needs to make a decision. And let me play this multi-robot exploration demo that was bachelor thesis in then more than 10 years ago. So in this setup, the robots sense the environment, decide where to go. These are the frontiers, and there are the locations where the robot are navigated. So they choose one of the navigation go, and then plan a path. Actually, it is planned. The path is planned during the selection of the goal to assess what will be the cost and make some long-term decisions. And then the robot is following the path. So this is relatively complex, and even it has been done in bachelor thesis, so in one semester. 10 years ago, it's still complex, and in this case the robot doesn't have any prior knowledge about the environment, only about the locomotion constraints, let's say. So the problem is how to deal with the real world complexity. And it is always the right question, and you should have the right answer, that we need to relax constraints and consider realistic assumptions. So what is needed to have a feasible solution? And this is very fundamental part of any design of robotic system. So switch to the notation, and this is very important, not only because of exam, but this will provide you the ground for the later and especially more advanced motion planning techniques. So we have a model, work model that describes a robot workspace. Its boundary determines the obstacles. So for simplicity, you can have 2D world, geometrical obstacles, and in a similar way, the robot is defined by its shape, by its geometry, and parameters like kinematics, and it is controlled by the motion plan. And what is very important for path and motion planning is the notion of the configuration space, C space. And it's concept that describes all possible configurations of the robot. And the robot's configuration completely specifies the robot location in the world model, including the specification of all degrees of freedom. And you can further consider other constraints on the robot motion. But in a 2D world, you can have a robot with rigid body in a plane that has free configuration variables. So it's a position x and y and orientation. So this is the difference between the world model and the configuration. And what we have, we have a shape of the robot, and we will denote it by A, for example, that is a subset of the world model that is being occupied by the robot for a particular configuration. So that we have a configuration Q from the configuration space, and we will instance the shape of the robot for this particular configuration, and that's the occupied space by the robot in the world model. So what is important that we like to find a path or trajectory in that is not colliding with obstacles. So, and we can define the C obstacle that is part of the configuration space where the robot is in a collision. So this is all possible configurations for which the robot is in a collision with an obstacle. So O is one of the obstacles among all obstacles. And what we are particularly interested in is a collision-free part of the configuration space. And this is the way how you can define the configuration space. So we have the world model and we have the obstacles in the world model. We have a robot that has its shape, and we have configuration space that describe all possible configurations of the robot. And we can easily define the C obstacle, the obstacle part of the configuration space, because that's all configurations that are at which the robot is with collision with obstacles. And if we subtract the C obstacle from the C, we will have the C free. That's not easy to explicitly define. So I will show you in a few minutes. So, but regarding the taxonomy or notation, so a path is a continuous mapping in a C space such that we have some initial location that we will denote 0 and the goal location we will denote 1 to the C free. So this is a curve, a continuous mapping of the C space. So we map the interval 0 to 1 to a curve in a configuration space. And we can consider that the trajectory is a path that is explicitly parameterized by a time. So we have further accompanied interval of time, but here the robot needs to follow the motion laws. So the U is a robot's action space, and this might include dynamics of the robot. So because this is a set of configurations that are reachable, that are feasible, that are not in a collision with an obstacle for the robot. But here we follow the motion laws. So we include the kinematics model, for example. So, and the path planning is a determination of this curve, and trajectory planning is a determination of the trajectory. It's parameterized by time. And we have additional requirements. For example, we ask for smoothness of the path because of trajectory. It must be feasible. The robot must be able to actually reach that. And additional are kinodynamic constraints. So we cannot move arbitrarily fast, or we cannot accelerate arbitrarily, because that we need to consider friction forces, for example. And of course, there is the optimality criterion. For example, we can ask for shortest path or fastest path. That means that we also need a velocity profile for that. And we will cover that in curvature constraint motion planning. So path planning is planning a collision-free path in a C space. And regarding this path planning and motion planning, you can be confused in the literature because sometimes these terms are used not very wisely. But we can define that, and we will consider that the path planning is planning a collision-free path. So it's a continuous mapping and C space. And motion planning is planning a collision-free motion. So this is a motion. These are the actions, and we can we actually plan the motion in state space. Just to clarify these two terms. So let's take a look to the planning in the C space, and we will have geometrical map with polygonal obstacles. That is a sequence of vertices connected by straight line segment. We have a disk robot, which is nice. And some start position and goal position, and how we can find a path in this environment. So we cannot reach any configuration because the robot will be in a collision, and we can imagine that if we will use the disk and put it to any or for all points of the obstacles, Then we will create a C space, because that's the space where the robot is in a collision. And this can be done by Minkowski sum. Basically, we enlarge obstacles by the disk of the A, that's represent the shape of the robot. And now we actually plan for a point robot, which significantly simplified the things. And that's one of the, so this is not the world model, even though that it can look like that, because that's still 2D, but it's a configuration space. And if our robot, in this case, is omnidirectional and its shape is a disk, we can easily create such a representation where we are not planning for a disk robot, but we are planning for a point robot in a configuration space, because these are C obstacles, they are not allowed. However, creating a explicit representation can be very difficult, and we can see in this example where we have a triangle shape robot. So we will consider a particular orientation of the robot and we will create the same, okay? So this is the reference point of the robot. But you can also consider another orientation of the robot, because that's the configuration space, X, Y, and theta. So it may look like this for all possible orientation. So, and a simple 2D object has a complicated C obstacle, and it is even more complicated the complement for the C3. So even in this case, the deterministic algorithm exists, but requires exponential time in C dimension. An explicit representation of C3 is impractical to compute, unless for very special cases. So now we will cover that in sampling-based methods in the next lecture. So, and one of the way how to address the complexity of the motion planning using the notion of C space is, and just remember, the C space is continuous representation. So we will discretize it, and we will find the critical geometrical events as using like sampling methods or roadmap or cell decomposition. So we will discretize the C space, and when we have a discrete representation, we can represent the C space as a graph, and then we can apply any graph search technique, like breadth first search, gradient search, A-star, and so on. And in this lecture, we will go through selected methods that are probably beyond the AI general courses or general graph search techniques, because these are specifically designed for path planning. But let's classify the path planning methods. These are the selected approaches. So first, it's point-to-point path or motion planning. And we will also cover, because that's essential for robotic information gathering, multi-goal paths and motion trajectory planning later. So, but for now, it's point-to-point path planning. There are roadmap-based methods. They create this connectivity graph of the free space, and the simplest is the visibility graph, which is complete but impractical. We will see cell decomposition or Voronoi graph-based approaches. And in addition to this roadmap maze with the critical event, we can consider discretization into a grid-based or lattice-based representation, which are, of course, you can choose what is the discretization, what is the grid size, so they are resolution complete. So for a particular discretization, you are able to find optimal solution, but it doesn't mean that in the there can be or there cannot be a better solution if you use finer resolution. And there are potential field methods that are complete for high navigation function, which is hard to compute in general. So let's say these are the classic path planning algorithms, and there is another large part of randomized sampling-based method, because they are they exhibit successful deployments in many practical cases, and basically these randomize, so they sample the configuration space randomly, but you can imagine that in some parts that are not important for our particular task, we will not sample. So we will sample where it is important. So the randomized sampling needs to have a proper distribution function for the sampling. And this is actually covered in a separate lecture. So just to remind what is the visibility graph, we have a problem represented as in a polygonal domain, which is a discrete representation, and we can find a visibility graph. So this is connection of all vertices that are collision free, and you can imagine that this problem is for point robots, so we enlarge the obstacles. And having such a graph, we can use Dijkstra or any other algorithm to find the shortest path. And you can create a visibility graph in a naive way with n cubic complexity. But there exists a more sophisticated method using rotation trees that has squared complexity. So if you are interested in, take a look to the paper or ask me for more details. And it's quite important concept to actually not pre-compute everything. This is also used in many AI approaches, and this is a representative of path planning algorithms that combines A star for planning with the visibility graph computation. But during the relaxation of the nodes and expansion of the nodes in the A star, we actually perform the visibility check. And as you can see in this minimal construct, efficient shortest path in polygonal maps approach, it can really speed up the process. And this is the squared, the rotation trees. So we are not speaking here about like naive approach. It will be much more demanding. So I will not ask you to know or remember exactly how this minimal construct algorithm is working, but the idea is important. Okay, what is not needed, we don't compute, and we will compute very lazy. So only once it's really necessary to decide where to go, which can significantly speed up the planning methods, and that's the general idea. So that's the reason why we have this slide here. So Voronoi graph is another example, and it's a little bit different from the visibility graph, because in visibility graph we have a shortest path. But we can ask for maximization of the clearance, because it might be the idea that once the robot is navigating in the middle of the corridor, it will not collide with the walls. So that's behind the Voronoi diagram, and so we can compute it, and then we will have a graph representation. So we will check where is the initial location, that's the end location, what is the closest short or closest collision-free path to the Voronoi diagram, and then we will in this graph found a path. However, I have some comments on that. Having like a robot which is in the middle of the corridor, if there is only one single robot, that's fine. But if you imagine that there are multiple robots moving in the corridor, or even humans, that's probably not that smart idea to actually navigate the robot in the middle of the regions. And there is ongoing research. Actually, my colleague Tomáš Krajník is working on that to actually predict what will be the stream of the robots, stream of the people, to avoid or plan a path for a robot that will be in line of the current majority of the movements in the corridor. So, but that's for completeness. This is also a usable method, but just think about possible drawbacks in more complex setups. And of course, the visibility graph and Voronoi graph can be combined, as has been done in 2004, visibility Voronoi. But for higher dimension, computing visibility graph is very demanding. The Voronoi graph can be done depending on the map representation. For example, for spheres, it's relatively straightforward. But for high dimension, we basically need other types of road maps. Cell decomposition is another method just for completeness. In some very simple cases, it can be fine, especially if you consider that on this path planning level, you will provide just rough course planning, and then you will have a local reactive controller. For example, using this LMGD with CPG, as we can see in the last lecture. So the decomposition methods decompose the environment to cells that are collision-free, and where we can easily find a collision-free path. Basically, any segment connecting any location here in this cell is collision-free, and in this trapezoidal decomposition, you can use this critical event. Then we split the horizontal part, and in the middle we will have another vertex, and this create the roadmap. And then we have a point. We will ask what is the cell, and then we can directly connect with the cell representant, which is the middle part, and follow the roadmap. Again, using some graph search techniques. And of course, it's not only one decomposition. You can use triangulation. But if you will ask what is the complexity, then you will probably, and you have the geometrical map, you may end up with pre-computation of some data structure that can speed up the queries. And one of them is shortest path map. So here we have a location, and we can pre-compute this data structure, shortest path map, that will provide us a quick answer what is the shortest path from any location in the environment to that location. So, and we have this shortest path map, and once we are here in this cell, then we go through these vertices, right? If we are, for example, here, then we can go through these vertices, right? And how this can be done? Actually, this is some cartoon. The idea behind is a continuous Dijkstra paradigm. So we propagate a wavefront, and we check the critical events. And these critical events is once we reach a vertex of the map, and there is other critical events where these front waves from one part and another part are merged together, and you actually need to represent it. It can be done, and there is also a two-point query data structure, which is more demanding. But basically, the idea is that once we have a map, we pre-compute something, create a data structure, and here we have splitting, it's decomposition method. So we create a decomposition of the environment to individual cells, for which we can quickly query the shortest path to any location. But you may ask, okay, how I will find the cell? So this point location problem. So you have some decomposition, and you are asking in which cell the location is, and what you can use is interval trees, and there is a really old paper about that. So you can just very rough idea that okay, you will create the interval tree of the x coordinates, and for each this slice you will create another interval tree with the vertical coordinate. So, and then you can quickly in log time on the number of slices and slabs answer the where the point is located. And you can also think about other type of shortest path and supporting methods. And here is example of using a navigation mesh. So we again split and decompose the free space, or in this case polygonal map, into cells. These are convex cells, and once you have a point location, so you know that I am here and I would like to go here, and so you identify that your robot is in this cell, but because it's convex, it is always a feasible collision-free path from the location to the vertex of the convex cell, and then you can have a pre-compute path from visibility graph to your location, destination. It can be pre-compute, similarly to the shortest path map. Having this, you can use some ray shooting technique or combined with working in a triangulation or convex partitioning, that you will actually ask, okay, so I'm in this cell and this is represented by double connected edge list, so you can quickly, without computing intersection, determine, okay, I'm passing this edge, but this edge is in free space, so it is possible, and same for this, so you can directly connect, and this is super fast. And when actually determining this, you have this line, supporting line, and you have this supporting line, and you are not asking, or you are not querying an intersection. You can just check if one point is on one side and other point is on the other side, which is a scalar multiplication, so which is easy to compute without any numerical issue. You can imagine that having such a relatively rough approximation using this convex decomposition, so you can improve the path by ray shooting. So you will also consider this in a grid-based method in a few moments. But the concept is that, okay, I have this path, so I have the convex region, so the collision-free is a direct connection of any point in the convex region to the vertex. We have the shortest path from the visibility graph, from the vertices, and then we can ask, okay, if there is a collision from this point to the first, this is the 0, this is the first vertex 1, and if so, we can shorten, and we can ask for a full refinement, and in this case we are lucky, so there is a direct connection without collision. So a practical implementation of this answer the queries in microseconds. So it's not, of course, it's not the optimal path. The concept of underlying decomposition with searching on top of that is also used in Polyanya algorithm that use a navigation mesh, and you can start with the grid mesh, and we can merge the grid and create the constraint Delano triangulation, and then we can merge it, which is sort of these convex cells, and the idea is pretty much the same, and you can this is relatively fresh algorithm, and you can find the method, the implementation available. So this is again informative and showing what are the current trends. So we have very old methods like visibility graph, and still this is the active field to actually find a suitable solution. In this case, mostly motivated, for example, in computer games. So artificial potential field method is a general concept that the idea is based on the navigation function. So we will create a potential field that attracts the robots towards the goal, and because we like to avoid the obstacles, we will create a repulsive potential to push the robot away from obstacles. So, and then basically the navigation or the path planning is that if we have any point in the environment and we have this navigation function based on this potential field, then we will just follow the gradient, right? That's super convenient. However, depending on the potential function, there can be several local minima, and what you can find in the literature is that if there's this typical example, you are stuck here and you will not reach the goal, because that's multiple local minima. However, if you will consider harmonic function, for example, which is expressed here, and you can compute the very same potential field method, and this is the visualization of distance, and you can, from the distance, you will follow the gradient, to the goal location and have such paths. And this can be employed again in multi-goal planning, as a master thesis, and combining this, and the robot will follow that. So, and just to make some comments on that. Okay, so you can have the artificial potential field with only one extreme. Once you will have a harmonic function, you need to properly define the Dirichlet and Newman boundary conditions, and that's a tricky part, because then you can experience problems with numerical stability. Okay, but that somehow can be addressed, and what you can see in this video is, okay, we have the goal locations here. We pre-compute the potential fields, and then we have the shortest path, and then we can solve the TSP on top of that. And what we gain, actually, what is the benefit, is that we have a smooth path. And what you can see here, it is actually path following. And here, okay, once the robots make a turn, it takes some time and maneuver to actually reach and follow the path, but it can be done.